Welcome, everyone. It's my great pleasure to introduce to you Kathy Whaler. She's our 2012 Edward Bullard Lecturer. I think most of you know that the Bullard Lecture is given annually at the fall meeting. It's part of the AGU Bowie Lecture Series. It started out in 1988. It was first called the Alan Cox Lecture and changed to the Bullard Lecture in 2002. And Kathy is our 24th member so honored by this lecture. Kathy received her PhD from the University of Cambridge in 1981, stayed on as a postdoc for a couple of years. She then became a lecturer at the University of Leeds. That was in 1983. And 11 years later became the chair of Geophysics at the University of Edinburgh. Along the way, she's worked at NASA Goddard, at Harvard University, University of California, San Diego as the Green Scholar, Victoria University, and other places. Kathy was president of the Royal Astronomical Society from 2004 to 2006. I believe she's still president of the IAGA, right? International Association of Geomagnetism and Aeronomy. She started that in 2011. Kathy's research uses geomagnetism to study the dynamics of the Earth's core and deep mantle. She studies crustal magnetization of the Earth, Mars, and Moon using satellite data, geomagnetic observatories, and repeat stations. Presumably on Mars she doesn't use repeat stations, but she also conducts magnetotelluric fieldwork to infer the resistivity structure of the crust and the upper mantle, and that's the subject of her talk today. Kathy is a fellow of the American Geophysical Union, a fellow of the Institute of Physics, and a fellow of the Royal Society of Edinburgh. But perhaps most impressive is an organization, I don't know the name of the organization, but it apparently has an appropriate authority for such things, has named a minor planet after Kathy. Maybe she'll tell us more about that. So Kathy's presentation today is titled Magnetotelluric Studies in East Africa. And without further discussion, I'd like to welcome our 2012 Bullard Lecturer.
Thank you very much for those kind words of introduction. It's a great honour to be invited to give the Bullard Lecture, particularly as I'm a grandchild scientifically of Bullard, in that Bullard was my thesis advisor's advisor. So that's another. So I was thinking about the connections a bit further. So here's Bullard, and what people tend to think about when they think of Bullard is probably the fit of the continents, or perhaps his studies of the Earth's core. This is an example at the bottom there of looking at the westward drift from looking at the drift of certain features in the magnetic maps. So where do I fit into that? Perhaps if you think about me and my research, and as Rick's already said in his introduction, crustal magnetization or flows on the Earth's core surface that explain the magnetic field evolution. But you've actually had quite a bit of that in terms of Bullard lectures for the last few years, so I thought I'd go for something different. And I took my cue from Bullard. So this is a picture of Bullard next to one of the East African lakes, where I believe he was doing some heat flow measurements with the kind of instrumentation that's shown there on the left. I haven't got any photos quite like that myself, but these are a few examples of me doing fieldwork in East Africa there. The top one there, I'm actually being a goat herd, but never mind, trying to stop them from eating our cables. So it's this kind of research that I'm going to just try and talk you through a little bit today. Obviously, many people have helped me, collaborated with me on this, including two large consortia, the EAGLE and the AFAR-RIF consortium. And we've been very heavily dependent, obviously, on support from local colleagues in all parts of East Africa in which I've worked. But that's particularly in Ethiopia from Addis Ababa University and the Ethiopian Geological Survey. So what I want to do is skim through the MT method. Now, those of you who are experts in EM induction are going to have to try to stop cringing, because I'm going to zip through it very fast, and I'm going to play a bit loose with it so that we're not tied up here for hours before I actually get onto some examples from the East African Rift. And what I'm really wanting to concentrate on is how we can use joint interpretation in the most cases for the examples I'll show you here, so we can get a lot more out of the data. So I'd like to show you how the kind of work that I've done fits into these larger studies and enables us to learn a lot more than we might from individual ones. And if I get time, I'll go into some wild speculation before a very brief summary at the end. Okay, so the magnetotelluric method is sensing physical parameter, the electrical resistivity, or its inverse, the electrical conductivity of subsurface materials. And the electrical properties of Earth materials are governed primarily by mineralogy and by fluid content. And the MT method is particularly sensitive to conductive materials. So that's things like non-organic fluids, magma, and partial melt. So you can start to see where I'm coming from with its use in the East African Rift. So that's what we've been using it for in a number of studies in East Africa, but also to do things like contrasting sediments and intrusive basalts, identifying stratigraphic units, probing aquifers, and for geothermal exploration. So magnetotelluric sounding is a passive measurement. So actually what we're trying to do is to measure the Earth's natural electric and magnetic fields. And so the signals are coming from the external environment of the Earth, from lightning strikes and solar wind interacting with the Earth's magnetic field. And you'll see a little symbol there, and I don't know if I can make this work. There we go. So, no, if I do, there we go. Just to break it up a little bit, that's actually a Whistler mode, which is a much higher frequency than the kind of frequencies that I'll be looking at in this particular study, but it's those kind of electromagnetic signals that are our source, our naturally occurring source. So what we do is we measure the magnetic and the electric field in two orthogonal directions, typically north and east, and from them we can derive the subsurface resistivity structure. And typically in East Africa, if you record for a couple of days, you can probe a few tens of kilometers down in the subsurface. So this is the schematic field layout. Basically what we're doing is, let me get my pointer here, is we're measuring the magnetic field in, say, the north and the east direction, or the north and the west direction as it's set up there, with induction coils. And if you want to go to longer periods than the kind of studies that I'm talking about today, then you would use fluxgate magnetometers. And then you just put in two pairs of electrodes, measure the potential difference between them, divide by the distance to get the electric field. And the separation would be something typically like 100 meters. Oops, sorry, going backwards. I know why, because my mouse is turned upside down. There we go. And this is what it looks like in practice. These are the coils here that we bury in the shallow subsurface to keep the wind noise down, and that's after very carefully orienting them and leveling them. This is burying one of the electrodes, and in fact we use a bentonite mud mixture to maintain good electrical contact between the electrode and the ground, and then sit around trying to see our computer screen in the blazing sun, which is often a challenge, so there's a need for an umbrella. And typically we'll leave these things powered by solar panels. So this is an example of the real-time data monitoring. So you can see the 2-second time window there. These are the 4 channels of the electric and the magnetic field, and you can see simultaneous bursts of energy in all 4 channels. So we'll apply calibration factors to those time series, and that will give us electric field components and magnetic field components. And you can see this is now a much longer time series, but again, you can see simultaneous bursts of energy in all 4 channels. And then we'll do lots and lots of post-processing to analyze the data in the time series are going to be analyzed in the frequency domain. Then we'll get a depth of investigation, which is going to be a function of the frequency, or alternatively the period, and of the resistivity. And we express that essentially as a skin depth, which shows you how it's proportional to the square root of the resistivity and the period there. So period is acting as a depth proxy in these studies. So what we need to do then is to calculate essentially the ratio of the electric and the magnetic fields, and those give us the components of these 4 possible pairs of ratios that we can get of a quantity that's known as the impedance tensor or transfer function, which is a complex quantity, and that embodies all the information that we get from our surveys about the subsurface resistivity. We typically express that in terms of apparent resistivity and phase, defined this way. So here's the apparent resistivity, here's the phase. Apparent resistivity, when we normalize the amplitude essentially by some factors here, including the frequency, has a units of resistivity, and it's the actual resistivity for a uniform Earth. And phi, then the inverse tan of the ratio of the imaginary to the real part, measures the lag between the electric and the magnetic field. And that's 45 degrees for a uniform Earth. So that gives you a yardstick against which to measure your actual field data. Now, the impedance tensor in the general form is given at the top here, but in certain geological situations, it takes a simpler form. So in the 1D case, you've got 0 along the diagonals, and then the off-diagonals are just one is the negative of the other. In a 2D case, again, 0 along the diagonals, but the off-diagonal elements now are unequal, and the 3D more general case. Now, this 2D case only applies if the axes coincide with what we call the geoelectrical strike. So this is the direction along which currents are flowing, or the direction perpendicular to them. So typically, of course, you don't measure that way. So what you do for a 2D model is rotate the impedance tensor into the direction that minimizes these diagonal elements, and then that rotation angle indicates the geoelectrical strike direction. There's many approaches to ascertain whether you can, for instance, assume that your diagonal elements are 0 to with a measurement error, i.e. whether the data are compatible with a 1D or a 2D or a 3D Earth. What we also need to worry about is shallow conductors on which charge can build up, and this will distort our data. So most of the examples I'm going to show you are going to be based on 2D modeling, where we've been able to remove most of the distortion effects by standard techniques, and alongside that determine the optimum electrical strike direction. Now, I'm not trying to suggest that my data are purely 2D, but I want to give you illustrations of what you can do, and I'll just use my 2D modeling examples for that. Okay, and in the case of a 2D Earth, then the data do separate into two independent modes, which we call the transverse electric, or TE, and the transverse magnetic, or TM mode. And they describe currents flowing parallel or perpendicular to electric strike directions. And then each of the modes is sensitive to different parts of the conductivity structure. Right, and we're just nearly about through the theory here. So we can, in a 2D case, plot what we call data pseudo-sections, and these are our apparent resistivity and our phase for the two off-diagonal tensor elements versus period t. And they'll give you a quick look, a visual indication of the structure. And those variations of rho of apparent resistivity and phase with period, i.e. with depth, indicate variations in subsurface resistivity. So phase angles greater than 45 degrees indicate resistivity decreasing with depth, and vice versa. And these phase changes are sensitive to resistivity changes at shorter periods than when we look in the apparent resistivity. So again, the combination of those two pairs is very important. Right, and then we need to try to invert our tensor information in terms of a subsurface resistivity structure. The mathematics shows you that the solution is highly non-unique. You need to parameterize a much larger area or volume than is sampled by the data so you can satisfy the boundary conditions. You set up block sizes that will increase with depth and with distance from the site. So the area outside the region of interest will be rather coarsely parameterized. And most strategies involve regularization. So you will, for instance, find the smoothest structure that satisfies the data. And a number of people, I'm really skimming through a huge amount of research here. There are various clever tricks to increase the speed and reduce the data storage requirements when you do these inversions, be it in 1, 2, or 3D. So let's go on to some examples now. East African rift system is going to show most of the field areas here from the Afar Depression in northeast Ethiopia through the Ethiopian section of the rift into where it splits into two, the eastern branch and the western branch. And I think if I click now, I'm going to show you, yeah. So this will be my first example. It's actually up on the Ethiopian plateau here, but it also mirrors another study that we've done down in the southwest corner of Ethiopia on the Ethiopian-Kenya border. My second example will be right down in the Kenyan rift itself. Thirdly, across the main northern Ethiopian rift, and finally into the Afar depression. Hopefully I'll get through them all. So this is the first example. Now we're up in on the Ethiopian plateau itself, where there's been vast expanses and vast thicknesses, several kilometres of tertiary flood basalts, but beneath them are buried some sedimentary basins which are being prospected for hydrocarbon exploitation. And those basins are quite often intruded with basalts as well, or intruded with some igneous rocks. And that makes them really quite hard to probe with standard methods like seismic techniques. But in fact, you can do something useful with magnetotellurics, as we've shown here. So what we've done is a profile of sites that goes along the edge of Lake Tana here. It's not an ideal arrangement, but it was where the roads were, so where we could get access to actually perform this survey. And then this up here is an image that we've got from the resistivity data going from southwest to northeast across the basin here. And as in all the images that I'll show you, high resistivities or very low conductivities are in cold colours, and low resistivities or high conductivities are going to be in warm colours. And obviously that works very well when you're thinking about fluids, where warm, hot fluids will have a lower resistivity or higher conductivity. But you can see here a very sharp contrast between the sedimentary, the sediments in the basement beneath, but also resistors cutting through them. So here's a schematic of how we've interpreted this model on the top. So you can see the basement down to a few kilometres. Here's in fact the flood basalts on the top here, rather thin there, but much thicker as you go into the main part of the province there, and intruded by these dikes and sills. So that was a quick start, and then we'll go now into the Kenyan rift, where you've got a schematic of the structure here, border faults down the side, and these transfer zones going across them. And we studied an area between Lake Baringo in the north and Lake Bogoria in the south. Now, over geological time, these lakes have been connected, they've been disconnected, they've changed their salinity from alkaline to acid and so on and so forth. So very, very complicated sedimentary pattern. And we put in a number of sites that you can see the splodges on the map here, and interpreted in 3D, in this case, the resistivity structure. And this is what we did with it. I'll show you on the diagram here. So these on the left are depth slices through the model, where the layers here indicate next to them the depths that we'd sampled, going through from nearer the surface to the basement. Previous work included some seismic reflection data, again for hydrocarbon exploration, so there's an example here. And that had been extrapolated across the rift to the east. But what we did was a reinterpretation of the stratigraphy on the eastern side by using the resistivities in our model layers to reinterpret that. So for instance, here you've got ringed layer 9, and that is our new interpretation of the stratigraphy in the layer 9 there. So by doing this, using the resistivity structure that we derived, we were able to produce a new log going across the basin here, and this is then a revised history of the sedimentation patterns that was inferred from there. Obviously, there was input from other existing data, like some of the structural mapping that went alongside this survey. But that's another example of things that you can do. How am I doing for time? Right. Okay, so the main things I want to concentrate on are two study areas in northern Ethiopia. So the first one was part of the Eagle, which was a cross-rift, well, it was more than cross-rift, in fact, set of surveys that were done around the early 2000s. So we're now up in the northeastern part of Ethiopia here, and you can see the very northern end of the main Ethiopian rift, where it's starting to divide up into the Afar depression to the north there. And this was one of our multi-discipline surveys that I want to talk about. So on here, you can see some red hexagons, which are our MT sites. So we did about a 60-kilometre profile across the northern rift here. Underneath them, coinciding with our profile but extending further, are the blue and the black triangles, which are seismic stations, 3-component broadband and short-period stations. So in fact, there was a profile that went across the rift here, and then another line that went along the rift there. And this was, we sampled this with a seismic refraction and wide-angle reflection survey using explosive sources that sampled this whole area. And on top of this, there was also a gravity survey. I'll show you the results from that in a moment as well. And you can see here that we've got border faults on the two sides there, but more importantly, we've also got these quaternary magmatic segments. So these are the grey splodges here outlined, and the blues are the rift lakes. Okay. And there was also some, the grey squares are showing permanent and previous broadband seismometers, and the previous ones were mostly from Andy Nyblade's survey from Penn State. At this rather late stage of rifting, the border faults have been largely abandoned, and most of the strain is accommodated in these magmatic segments, which are actually, as you can see here, arranged in an on-echelon arrangement. So that's the basic setup of what we did. You can see that there's quite a large change in elevation as you go along this line. This site, most northerly site here, was about 3,500 metres. Right down into the rift, you're below 1,000 metres. But it was relatively slowly varying. This is a very gentle topographic slope to the south, sharper, sorry, from north to south here, sharper on the southern side of the rift. So this is the 2D model of our profile here. I just said it was 60 kilometres. It was a lot more than that, beg your pardon. Site stations were about 20 kilometres there for the main part, and we tried to make them much higher in the rift itself, where we expected to encounter higher resistivities. So you can see that we've actually got, well, to the south of the rift here, we've got much higher resistivities. We've also got a band of relatively high resistivities here. We've got sediments on top, which I'm prejudging the interpretation here. And then a number of conductors in the subsurface there. This is in the deep crust, as I'll show you in a moment here. Because, as I said, there was a controlled source seismic model. So you can see that the MOHO here is going from about 40 to about 48 kilometres, and that's below sea level there. Okay. What the seismic refraction survey found was that there was a layer of underplate, the crust here, on the western side of the rift, but not on the eastern side of the rift, and in fact obviously some other structures here. So what I'm now going to show you is a comparison between the two. So this is now the seismic model in the pastel colours underneath here, with their layering, and in fact showing you the sampling that gave you that structure, and then the MT model on top. And you can actually see that our conductors here are in the lower crust and extending a little bit into the underplated area. So this is suggesting that there's actually possibly still some molten material left in the underplate or in the lower crust immediately above it. And then these very high resistivity structures are in the much shallower subsurface here. And we've also got one of these conductors here is below, in fact, a volcano that sat in the middle of the rift on one of those magmatic segments that I pointed out earlier. And you can see nicely, I think, the good comparison between the MT and the seismic when we go across the border here into the plate on the other side. Okay, so I mentioned that there was a gravity survey done, and this is now the gravity model. So here's now density in grams per cc. And this was actually taking the seismic model and just modifying it as was necessary to make it fit the gravity data as well. So they used that as their starting point. And basically they ended up having to put in a number of gabbroic intrusions here to fit the density that they got in certain places. And this is also what Katie Karanan and co-workers deduced from their along rift profile as well. So you see these intrusive bodies below the rift itself. And you can see how it slopes in from the north to the south, and then we've got much sharper border faults on the southern side of the rift here. And again, you can see there's a good correspondence between here, the gabbroic body here below the rift itself. This one doesn't show up as well, but this one is actually, I would say, would be a better way to model this change here than the structure that they've put in there. The other thing that was done as part of this was looking at the relative residuals from the seismic stations here, and you can see that the eastern flank here is clearly much faster than the western flank here. You can see the residuals are decreasing. They've gone negative here as you've gone across into onto the Somalian plate to the east. And again, that fits very well with our very sharp change in structure as we go across the rift boundary here on the southern side. Now, I mentioned when I talked through the theory about the geoelectrical strike direction, which is the direction that you can that minimizes those diagonal elements when we are trying to do a 2D interpretation of it. So you can actually plot those geoelectrical strike directions, and this is just a choice of those strike directions of particular period, because they are both period and site dependent. And you can see, and you might need to use an eye of faith to some extent here, but you can see that they roughly parallel the rift border faults on the plateau, both on the Somalian side and on the Ethiopian side. And they rotate slightly further to the north within the rift to parallel the en echelon magmatic segments. And this study was prompted by noting that the seismic shear waves splitting fast directions do the same. So here again are the seismic stations that they were able to interpret the anisotropic signature from it. So this is a single wave going in, polarized into a fast and a slow component going out. So the direction of the arrows here is the fast direction, and the length of the arrow is the amount of the time delay between the fast and the slow phase. So you can see here how the anisotropic fast direction rotates to parallel the en echelon magmatic segments within the rift itself and off onto the plateau on either side. It's actually parallel to the plateau there. And the interpretation of the seismic anisotropy is orientated melt pockets in the lower crust. So this actually fits with the period at which these geoelectrical strike directions were plotted. Okay, so the last part of my talk, which I wanted to spend the most amount of time on, and seem to have got the timing roughly right, is to move into the AFAR, where I've been working since for about the last 5 years or so, as part of the AFAR Rift Consortium. And this work was prompted by a mega dike intrusion in one of the segments, this Debahu magmatic segment shown here. And again, you can see the magmatic segments. We were looking at the area down here just now, and now we're up in this part of the AFAR depression itself. And it's been the start of a diking episode, which I think has had 14 dikes that we've been able to monitor to date now. And we've been out several times into this area to try to do a number of studies, including magnetotellurics. I'm showing a bit more of the structure that's going on here. So relative to the Nubian plate, this is 15 millimeters per year. So this is a slow spreading ridge, basically. This is a rift triple junction. So you've got the Red Sea rift here, the Gulf of Aden rift here, and the main Ethiopian rift coming in here. So this is essentially a triple junction point. This part is basically on the Arabian plate. The Red Sea rift ridge jumps on land around here and comes in through these magmatic segments here. There was an earlier diking event that's been quite well monitored in 1978, but of course that predates the satellite era. The advantage of what we've been able to do is that we've been able to use a lot of remote sensing techniques as well to study here. So that's a 15 millimeter per year spreading rate, and Somalian plate is separating from the Nubian plate at about 6 millimeters per year. But this is the bit we're interested in now, at the slightly faster but still slow spreading rate. And you see again Pliocene now flood basalts covering much of this whole area. The other thing that is marked on here is this discontinuity that's basically separating the main Ethiopian rift from the AFAR depression. So we're well within the AFAR depression now. Okay, so the first hint of what was going on came from, in fact, the seismic records that were, this is monitored at the Geophysical Observatory at Addis Ababa University. So you can see on the bottom here, sorry, this is a seismogram from the 14th of September, and this is the one from the 24th of September. So clearly something extraordinary was going on. So they were able to mobilize a field team to go out to the area. And this is what it looks like up there. You can see all these very marked faults dipping into the center of the rift there. And this is what they found. There'd actually been an eruption. There's a gash here. Here are people for scale, so you can see the size of things. A relatively small eruption, but this had opened up as well. Lots of ash and pumice covering the area. And huge amounts of movement on some of those faults. So there's a pre-existing scarp of 18 meters high and a new 3-meter throw that you can see showing up as the very pale colors there. And this is actually close up to one of those where you can see the offset. So it's 1 to 2 meters laterally and about 3 meters vertically, associated with the event that was causing the seismic madness, as it were. So they also got hold of some INSAR data, and they were able there to show that there was a megadike intrusion. So by megadike, we mean it was in 2 weeks along a 60-kilometer segment here. It was about 2.5 cubic kilometers of material injected. And as I said, there's been about a half a cubic kilometer since in a number, up to 14 further dikes, and a couple of near surface eruptions as well, but mostly it's been subsurface. So this whole segment was active for these 2 weeks. Where we were before was up around Debahu volcano. That's going to be an important thing in the story to come, as is the Badi volcano here and this Adawali volcanic complex here, which has been separated by subsequent rifting. So that's, we were then able to get funding to go and do a fair amount of work on this area. And basically, of course, with all this dike injection, that means there's got to be a huge amount of magma around. So my task with the magnetotellurics was to try to map out where that magma exists and do a little bit more with it than that. And this is just showing you again seismicity. Immediately after the event, they were able to go out and deploy seismometers. So this is now mid-October, less than a month after the thing happened, through to the following March. And you can see how the seismicity lines up on the segment there. So these are magmatic dike-induced seismicity and fault plane solutions showing normal faulting, as you would perhaps hope to see. Okay, so over a number of field seasons, this is the area that we've been looking at. We've tried to do a contrast between a profile across the active segment here, just to the north of this Adawali volcanic complex I was talking about earlier, and also for comparison, a profile across an inactive segment to the south here. That's the Hararo magmatic segment here. And we also got the opportunity to just take a few sites up along the road here, up towards the Debahu and Gabho volcanoes at the northern end of the segment, where that eruption happened at the start of this episode. And as I said, it was a very multidisciplinary effort, so that alongside the MT, there's GPS, as I've also mentioned, seismic stations, petrological sampling, structural and geological mapping, hyperspectral imaging, INSAR, other remote sensing, gravity, and paleomag sampling. So I'm not going to be able to talk about all of those, but I'll try and put some of the story together using multiple techniques. So first of all, we're going to look at, sorry, I think I've still got something out of sequence here. Right, let me try and go back. I've got my mouse upside down again, that's my problem. Okay, so the first thing we're going to do is look at the profile across the active segment here. This is the first one that we did. Sorry, I'll get there in the end. And this is from west to east across it here, so going from this through to here. Again, the colour scale, as we said before, warm colours, low resistivity, high conductivity, cold colours, more resistive material. Superimposed on it, to give you a bit of orientation, is the MOHO as determined from seismic receiver functions, which are the wiggles shown here. Seismicity within plus or 5 kilometres to the north and south of the profile, and the dike intruded zone that they've been able to map very well using the INSAR data as well. So you can see that there's a very strong conductor here straddling the Moho, and a shallower conductor here in the mid to lower crust. And they're mostly resistive material above it, less resistive material on the eastern part of the segment, and there's also a very, very strong conductor in the near surface as well. And of course, what that's done is had the effect of reducing our sampling depth by the sort of the skin depth arguments, but we are still able to resolve really to the bottom of the model here. So this is the best fitting 2D model of resistivity parameterized into blocks. And as you can see, the block size gets bigger with depth, as I said before. So this is a bit of interpretation here, and I've marked on it the rift axis, where the seismicity associated with the dikes that go in between these two red marks are shown. And you can see how this shallow magma chamber, which was inferred from the INSAR, has been mapped here, or this will be our interpretation of it being mapped here. Saline-rich fluids in the intensely fractured and faulted basalt and some sediments below is our explanation for this very shallow surface conductor. And there's plenty of evidence for fractionation in the presence of brines. And the area further to the north and the east has got economic salt mines. So this is consistent with the known information we have. And then we seem to have a mantle-straddling magma chamber here, or magma reservoir here. And I suggested that it's feeding the dikes, but I've put a question mark after that, and we'll see why a little bit later on. But so this is our basic interpretation of this first profile. We've done a fair amount of modelling testing on it, which I don't want to show you, but I'll just indicate the surface, the conclusions from that. And that's that the top surface depth of both of those strong conductors are well constrained. The base of the mantle-straddling magma chamber is affected by the model regularization. That's the smoothest model I've shown you that fits the data. So that tends to smear the structure vertically. However, we know that the base is definitely sensed by the data because we can see the changes in the phases at the longest periods, and at the sites where we've got periods going out to a few thousand seconds, we can also see those changes in the apparent resistivities. And tests show that we can't make that base any shallower than 30 kilometres. And bearing in mind that the Moho there is 22 kilometres or so depth, then we've got a substantial conductor in the mantle. And what you can also do is calculate the vertically integrated conductivity, or the conductance, and that's less affected by this regularization problem. And that's equivalent in this area to at least 4 kilometres of seawater, which is exceptionally high. So now I'm going to show you the result of this oblique profile, which is up towards the Dabahu volcano on the main road here. Now this is a little bit harder to model because in this case, of course, you can imagine that our profile is perpendicular to the main strike direction, which also turns out to be the geoelectrical strike direction. They're a little bit more complicated here for 2D modelling. I'll show you it anyway. And now you can see that, in fact, there's large volumes or large areas on this map here, or this model here, that are essentially white. So they're right down at the very, very low resistivities, incredibly high conductivities. And that would indicate enormous volumes of melt in the crust and probably down into the mantle. If you contrast it with the profile across the inactive segment to the south, you can see that there's a lot less magma around. Okay, there's a much cooler colours in general. There is a conductor. It's Moho straddling again because the Moho depth hasn't changed very much when we've gone that far south. But in general, we've got high resistivities, so much less magma, and there's no real evidence for a substantial subcrustal magma chamber. There is a little bit of melt down there in the mantle, but nothing like we saw before. And once again, you can see the saline fluid effect in the very shallow subsurface as well. And here there are, in fact, sediments on the surface as well, so it's not surprising that this reaches right to the surface. In the previous one, it didn't, although it was hard to see on the at the scale that we were looking at. Now, that's the suggestion of such large amounts of melt in the deep crust and the upper mantle is a little bit hard to reconcile with current ideas of what's going on. So I want to show you some of the supporting evidence for the existence of this deep crustal or upper mantle magma reservoir. And certainly for a start, we've got the receiver function, which is the ratio of P to S seismic wave velocity, which is 2.1, which is very, very high. Anything over 2 is remarkably high. And this is caused essentially by having a very low shear wave velocity, i.e. with having plenty of fluids around or partial melt. So this is, again, consistent with lots of melt. The shallow seismicity has been used to study the VP-VS ratio in the upper crust, and there it's only 1.8, which is basically normal. So the lower crust has got to have an even higher ratio than 2.1 to get the full crustal average down to 2.1. So we must be having vast amounts of magma. And this is a quote from Cindy Ebinger. So the lower crust must be dripping till we get the crustal average to 2.1. There's been quite a lot of work done on the GPS data, and one study suggested that we've got a 10 to 12 kilometre effective elastic thickness crust over a low viscosity layer, which could be a partially molten crust. And that fits with the top surface depth of the conductor on the model I was showing you before. And I'll show you in a moment, I'll show you some receiver functions, surface waves, and PN velocities as well. So this is the receiver function study over several profiles. The one of interest for us, here's our Debahu active magmatic segment, the green one here that I'm just about getting my pointer not too shaky to point out, that's the Hararo segment. So this line C dash goes across, is basically coincident with our profile in the middle part of it here, which is this part here, where you can see they've interpreted crust with partial melt to explain those very high VP-VS ratios. And to the east, we've got stretched and heated crust, but a lot less partial melt around there. And this is the image across there, so it's this bit that we're looking at. And again, you can see the attenuation of those receiver functions caused by large amounts of partial melt there. So this is the surface wave study at a number of periods, so 5 seconds right through to 16 seconds, and right through to 25 seconds, I beg your pardon. So the panels are all organised 5, 8, 12, 16, 20, 25. 25-second period waves probed to about 30 kilometres depth. Now I've put our box just on this area here, so it's not obscuring the structure, but you can see in these shallower studies here, shallower periods that sampling the shallower depths, that you've got very low velocities. So here's the relative velocity, and it shows you what it's relative to from an average model there, showing again very low seismic velocities, which are consistent with partial melt there. And this is the PN velocity. This is the phase that's refracted along the MOHO, so it samples around the MOHO where we see our magma chamber. Grey areas are where the uncertainties are rather large. Here again is in fact our sites are shown on here. So this is the profile across the active segment. Here's the profile across the inactive segment, and you can see that the profile across the active segment corresponds with a very sharp decrease in PN velocity there. And this one down here is still decreased, but less so. So again, it's consistent with lots and lots of melt here, some melt, but not as much down here. So we've got a very substantial PN velocity reduction, which again is indicating extensive melt, but now in the upper mantle, because that's where the PN velocity is sampling. Okay, so that's great saying, yes, we've got lots of melt. What might be more interesting to try to quantify that a bit. So what I'm going to do now is to try to interpret those resistivity values that we have in terms of the amount of melt that's necessary to explain the data. So we've got lots of melt, so we would expect it to be well connected. That means that the bulk conductivity depends on the melt amount, the melt conductivity, and its geometry, but it doesn't depend really on the host rock conductivity. So those are the things that we need to know. Now, if I were to take published values of basalt melts, I would interpret the amount of melt in that at the center of that deep crustal upper mantle conductor as anything between about 8 and 60%. So that's not particularly helpful in terms of a melt amount. But in this case, we've got very strong constraints from the petrology, which provide basically all the things that we need to interpret the melt conductivity. That's the temperature, water content, silicon and sodium content, and also the depth, i.e. the pressure, which gives us then the melt conductivity. So the values that I've just done, we've been using for this are taken from Pommier and Letron's SigMelts, which is basically an online tool where you can just put in your content of water, silicon, etc., and out pops the melt conductivity. So I just thought I'd show you where those petrological samples have come from. There's been a huge amount of work done on the Debajo volcano, which has got incredibly variable composition over a number of thousands of years. But that's given us data like melt inclusions from which we can get water content. Adoali volcanic complex has been sampled, and this is the area where there have been a few eruptions associated with the diking events. So these are very recent samples, and then a large amount of work done on the Bardi volcano. So we've had to extrapolate the values that we've got from the active segment here to interpret the inactive segment as well, but they should be compositionally similar, so we hope that's going to be okay. So we know it's well connected. We know the petrology provides the composition and therefore the melt conductivity. And because it's well connected and because we want to try and get a minimum amount of melt, we've used a parallel bound rather than a Hashing-Strickman upper bound, which is basically two different assumptions about the geometry of the melt to provide the minimum amount of melt from the bulk conductivity. And this is consistent with orientated melt pocket seismic anisotropy, which was the explanation for the Eagle data across the main Ethiopian rift, and as I'll show you later, also with the data from this part of Afar as well. So this is just to remind us what's happening. We've got an incoming seismic wave that's split into a fast and a slow one, with the fast one lined up with the oriented melt pockets. And of course, electric currents will flow more easily in the direction aligned with the melt pockets. So you'll get then a lower resistivity for the same melt fraction than if it was randomly orientated. So that's the assumption that's gone into what I'm about to go through. Okay, so this implies at least 12% melt. And it also enables us to put a lower bound on the volume of melt in that deeper chamber, which is what I'm going to try and do now. So what we've done is we've converted the resistivity contours into a percent melt contours. So this is the outline of the area that is 4% melt or greater. So this is the mantle straddling magma reservoir, and this is the shallower one that actually extends just about to the base of the crust there. And this is the resistivity value that corresponds to from that petrology. And then nested within it is an area where you've got at least 10% melt. And somewhere in the middle here is this 12% or so maximum amount of melt that we must have there. So we've got the melt distribution in the model. How do we extend those 2D models to get a melt volume from the area? So our 2D modeling assumption implies that the structure continues along strike to infinity. So you could assume that, as far as we're concerned here, to infinity is to the ends of the segment, which is sort of 30 kilometers in either direction, or spherically symmetric. And obviously, if you assume they're spherically symmetric, then you're going to, again, get a minimum amount of melt. And if you do that, then you're going to infer that there's at least 200 cubic kilometers of melt beneath the segment there. Now, what are the implications of that? That means that there's enough to feed activity at the current rate for 400 years, because we've got 2.5 cubic kilometres in 5 years. The current events are only every 400 years or so, however. So another way to think about it is, well, we need to build the 20-kilometre or so thick crust at a 20 millimetres per year. I mean, I know that the one I showed you before had 15 millimetres per year, but that order of magnitude far field spreading rate, and that provides that there's enough melt down there for 10,000 years. I'm kind of getting close to the end of my time, aren't I? So I'll show you also a little bit more about the electrical anisotropy, which is where we're looking both at the direction of the geoelectrical strike direction, but also the amount of phase split. So these are the apparent resistivity data, and here are the phase data down here. And the amount of split between these two phases is an indication of the electrical anisotropy. And as you can see, it's period dependent. There's no split at all at short periods, and then it opens out at longer periods. So you can actually plot that, and that's what's done here. So this is the period range of the MT data superimposed on the seismic data, seismic anisotropy data here. So we're going from 0.1 second to about 1,000 seconds here. And you can see that there's some correspondence between the seismic anisotropy and the electrical anisotropy, although of course it's not uniform. And here, the seismic anisotropy is thought to express the far field spreading rather than any oriented melt pockets, which are really confined to the axes of these magmatic segments themselves, the rift axes. And you can see how these things vary with the amount and with the direction. So the yellow is the local earthquake seismic fast direction proportional to the percent anisotropy. Here's a scale for that. And here's the splitting between the two phases. So this is a 10-degree reference bar here. And then we try to map out where those occurred by looking now at a data pseudo section. So here's the model, here's the data that are providing the information in that model. So we can see that these C's and D's here are where the biggest phase splits occur, and that's at middle to lower crustal depths. And that's actually slightly more specific than the depths that you can infer from the seismic anisotropy. So geochemists prefer to see their melt-in sills. Geophysicists put them in blobby structures because of the model regularization. But in fact, it turns out that if you put a sill-like arrangement here, so obviously this is nothing like sills because it's just using the parameterization of the model that we had. But if you do that, then you can make this area more conductive. You can see it's more conductive here than in its equivalent in the regularized model here to compensate for these resistive blocks here. And if you do that, you can basically get as good a fit to the data as we had before. I realise you won't be able to see this. It's not a good enough reproduction. It's all far too far away. But the data here, again, are the splodges. The reds and the blues are the two phases. And the two lines are, in fact, the model that's obliterated now and the blobby model on the right there. And, in fact, there's very, very good agreement between the red curves. The blue curves don't do quite so well because these are the ones where we should be varying this. We've actually just fixed it at 1,500 ohm meters. If we varied this, we'd get a very, very good fit to both phases by a sill-like model as well. Now, geochemistry, as I said, there's been quite a lot of work done on the Bullard volcano, which is basically lying near our conductive structure, and on some of the rift axis volcanoes. And they show that the melt occurs at about 75 kilometers, between 75 and 100 kilometers. So that's where you're actually getting the partial melt done. And analysis geochemically of these rift axis lavas show that they ascend very, very rapidly. But the lavas associated with the Bullard volcano near our main conductor actually re-equilibrate around the base of the crust top of the mantle here. And so our data are actually our model is actually quite consistent with what the geochemists are telling us. So this is the model there superimposed on it, showing where the geochemists suggest that the melt accumulates and re-equilibrates before it erupted, is where we're seeing our conductor there. And then this is the most shallow one where magma is only residing very, very briefly. Structural interpretation. Oh, sorry, there's one other thing I meant to say about that. So earlier I said, are these two connected? The answer is probably not. We're not able to tell whether there's a conductive pathway through here. Our data just aren't precise enough, but the geochemists would say that these are actually two separate reservoirs. I think I'd better skip this in the light of time because we're very much running out. But we've compared our work also with the structural patterns that are mapped here. And again, there's an element of good agreement. And I'm going to skip also the wild speculation part as well. I think this will be going up on the web, so if anybody wants to look at the slides, they're very, very welcome. There's some comments that go along with it. But we're trying to see if we can do some forward modelling of thermal implications from the very, very high conductivities we see around the Dabahu volcano to compare with the MT data to see if for instance, we can distinguish between dikes that extend well into the mantle and dikes that are confined to the crust. It's probably taking the data a step too far. I suspect we won't be able to distinguish, but it's an interesting application as well. And this is taking into account then that as these magmas cool, their composition changes as well, so therefore their conductivity changes. So the AFAR conclusions is that there's lots of magma beneath the active segment, especially up and around the Dabahu volcano. There's a substantial mantle reservoir, magma reservoir between the mid-segment profile, displaced to the west of the rift axis. And this deep chamber has been imaged for the first time. It's not at a depth that's susceptible to INSAR and things like that, particularly as there's not much magma movement out or into it, so that you don't see any surface displacement associated with it. And we've been able to put some constraints on the amount of magma it contains, and we've been able to show that it's definitely, at least partly, in the mantle. And then there's much less magma beneath the inactive segment, particularly in the mantle. So these earliest schematic models showed sort of possible magma chambers here beneath the Dabahu volcano and beneath the mid-segment here that were lying at around the crust-mantle boundary, and so those question marks can now go away. So I'll conclude here that MT is a powerful tool to image magma and partial melt, also things like contrasting sediments and intrusive basalts, identifying tectostratigraphic units, probing aquifers for geothermal exploration, and obviously plenty of other things as well. Thank you very much.
Thanks very much, Kathy. Before we go to questions and comments, we have just a formality here. For that wonderful talk, she gets this shiny piece of paper from the American Geophysical Union, and specifically from the Geomagnetism and Paleomagnetism section. So, Kathy.
Thank you very much.
Thank you. And one other little formality, I want to remind everyone in the audience that the Geomagnetism and Paleomagnetism reception and business meeting is tonight at 6:30 in the Intercontinental Hotel. So, questions and comments for Kathy?
Sorry, it's impossible to see.
We can't see you, so.
You just have to go for it, I think. Basically, what they do is they restrict the penetration. Oh, sorry. Yes, somebody was asking about how much what restrictions on the data do those saline fluids in the very shallow surface impose? And basically, what they do is they really hammer the penetration depth. So with the periods that we get normally, I mean, if I was to do this in Scotland or something, I'd sort of see halfway to the centre of the Earth. Well, I mean, that's a vast exaggeration, but easily 50 or 100 kilometres. And there, we're sort of struggling to get to 40. Well, we get to 40, but we don't really get any further.
Well, I have a question.
Oh, yes.
Okay, so in the mid-ocean ridges, if we look at the slow-spreading centers, most of the time there's no melt there, there's no magma, it's an intermittent process, and obviously the spreading rates are more like slow-spreading centers in that sense, but our fast-spreading centers, we have a continuous magma supply, and here it sure seems like you have a lot of melt. So what is this more like and why?
That's why I was trying to work out how long it would supply, building the crust for. So, I mean, this would suggest that these are intermittent for maybe a few tens of thousands of years. I mean, the actual activity on a given magmatic segment just will last for a decade or so, typically, and then die down. And then during that period, you're getting 10 meters or so of opening. And then it all decays away. So at the far fields, you're still getting your sort of 15 or 20 millimeters per year. And it seems that the plumbing is quite dependent on the availability, of magma, and that seems to be having an impact on the process if the contrast between the active and the inactive segment is valid that we've done from that. So it seems that somehow or another we've got magma around for a period, and it doesn't look like we need to extract anything like all that's available to fuel the dikes that have actually been injected in this episode, and you would assume therefore in other episodes. But So there are some studies of slow-spreading ridges where you do see some of this type of behaviour, and that's probably particularly where they're influenced by mantle plumes, which of course is the situation here. So that's probably the closest analogy, is slow-spreading influenced by plumes. Yes? It definitely does seem to be on the west. There's nothing from geodetics that I'm aware of, but there's some so far unpublished seismicity tomography, which has, again, slow velocities at those depths on the west. In fact, the correspondence in the depths is extremely favourable, so we're hoping that will be published soon as well, so we can draw on the analogies there. And I think there's some evidence in our model there's a different structure to the east of the rift again, like as is seen in the seismic receiver function study. And people have speculated about rift jumps and things like that in the past, which is a feasible explanation for it, but I think it requires more careful thermal modelling to decide whether that's actually a genuinely acceptable explanation. So.
I think we should wrap it up. The next group is ready to take the stage, and if we don't get out of here, they'll attack us. Let's give Kathy another round of applause, and we'll see you tonight. Thanks very much.